For this circuit, we need to write the differential equation governing I sub L of t, the current through the inductor. Now, since we need a differential equation, we want the voltage-current relationships for the inductor. So, if this is the current I sub L with this sign convention, the voltage across this inductor will have this polarity. Positive current is entering the assumed positive voltage terminal, and the voltage will be L, or this inductance, 4 henries times the derivative of I sub L with respect to time. Now all we need to do is KVL, KCL, and Ohm's law. Let's call this node A, and the first thing I'll try is KCL at A. We have U of t entering. If I assume positive currents are leaving, that's going to be a minus U of t, plus the current through this 3 ohm resistor is going to be this voltage, which I guess I'll call that V sub A, which will be a function of time over 3 ohms, plus this current through the inductor, which is just I sub L of t, and that sums to 0. Now that's a perfectly good equation, except it's one equation in 2 unknowns, V sub A and I sub L. We need another equation. KVL through this source isn't going to help much since we don't know the voltage across that source. It'll just introduce yet another unknown. So let's try KVL around this loop here. So I have a minus V sub A plus the voltage across this inductor is 4 DIL of t by dt plus 6 ohms times the current through here. If I apply KCL here, this is also I sub L of t is equal to 0. Now I can solve this for V sub A, and I'm going to get lazy and drop the explicit functions of time. So taking this on the other side, this is 4 DIL by dt plus 6 I sub L. Now I can plug that in up here, taking U of t to the other side. So U of t is equal to 1 over 3 ohms times this V sub A, 4 DIL by dt, plus 6 I sub L, and plus another I sub L of t. And that's a perfectly legitimate differential equation governing I sub L for t greater than 0. It's always a good idea to check our results whenever we can. So let's take a look at this differential equation and see what happens if U of t is a constant and we let t go to infinity. So we're looking at a very special case and seeing what happens. If this is a constant and t goes to infinity, then I sub L has to be a constant too. The homogeneous solution will have died out. We only have the particular solution, which has the same form as the forcing function. If I sub L is a constant, DIL by dt is 0. So let's call U of t a constant capital U. That's 2 over 6 I sub L plus I sub L. So this is going to be 3 I sub L as t goes to infinity. So I sub L at infinity for a constant input is going to be U over 3. Now we also know that if U of t is a constant and we let t go to infinity, the inductor looks like a short circuit. So physically our circuit becomes this. This is a capital U, so let that be our constant U of t. I have a 6 ohm resistor. I have a 3 ohm resistor. As t goes to infinity, there's no voltage across the inductor, so this looks like a short circuit. This is 6 ohms. And this guy here is going to be I sub L as t goes to infinity for a constant input. So now this just looks like a current divider. So I sub L at infinity is the total current, U, times the other resistance, 3 ohms, over 3 ohms plus 6 ohms. That's 1/3 of U. And those look like they check against one another. So now we can be pretty happy with this differential equation before we go to all the work of actually solving the differential equation if we're ever given an actual function for U of t.